introduction. And first of all, I would like to thank the organizer for organizing this wonderful workshop in this amazing town. I'm very happy to be here, and also thank for the opportunity to give me this presentation. So this will I will talk about the joint work with Hao Zhongchen and Frederick Dubris. Hao Zhong is at National Taiwan University. Frederick Dubris is at the University of Montreal. So originally I want to talk a little bit more overview talk on various applications of complex interpolation in quantum information. But after I see this seminar room with these very nice blackboard sets, I decided to talk more specifically. So I want to focus more on this application into quantum decoupling. Now I want to illustrate this idea very briefly. So let's suppose we have a quantum channel from A system to E system. So this is a CPTP map. Then if we are given a bipartite state, that's with the input system of the channel and with some reference system R, we send through the channel acting on the A, and it does nothing to the reference. Then it will output some states which is bipartite and may still be correlated. So an idea of quantum decoupling is that try to find a local unitary at A such that if we first, before we send it through channel, if we first do this local rotation, acting on A, then we apply the channel, and we hope the output state is very close to be decoupled in the sense that it's very close to a product state, and you can accept some epsilon error in the distance. So that's the idea of quantum decoupling. Let me give a typical example. So suppose our A system is a copy of two identical systems, and our channel is just taking partial trace to the first system, and our input state, bipartite state, is a dummy state on A1 system. So this is tracing out the first system, and we have a dummy on the A1 tensoring with some entangled state, let me write phi, between A2 and R. If you apply the channel directly to rho, it's clear that you are tracing out these dummy states and left with the entangled part, so which is still correlated. Or what we can do is that before we send through the channel, we apply some swap operator between A1 and A2, so that you swap the entangled part to A1 and you apply partial trace A1 and you disjoin the correlation, so you will get this tensor product. So by a local operation, then this decouple, you can have a perfect decoupling. So that's this idea of decoupling. It has many applications in quantum information, including randomness extraction. And here I'm going to illustrating the application in quantum communication of using quantum channel. So suppose we are given a channel N from A to C system, and it will admit some stand spring dilation basically we will have a isometry from the inputs to the outputs together with some environments, such that if we trace out the environments of this isometry, you get a channel. And this environment part is called the complementary part, which has appeared in Jason's talk. Then the idea of quantum communication is that suppose we have some quantum states, we want to send through the channel A, but to track whether we have faithfully sent through that, we always assume our state at the beginning is a pure state, so you have some reference system. This reference system in the whole process is not changing. And then the A parts, of course, we send through the channel. And let me now, using this partial isometry, using this isometry to indicate both the channel output and the complementary, or the environment side. So since this is just a isometry acting on a pure vector, a Hilbert space vector, so at the end, if we're connecting all the system, we know this omega should also be a pure state if we including the environment together. And then now, if we assume our channel outputs is sufficiently decoupled with the environment, so if this one is very close to the reference with the channel output and decoupled with the environment, suppose such error is small, and we know that there's only way that a pure state can be a product state, that's the product pure state. So then you will know that this part will also be proximately pure. And then you look at the at beginning, this VAR is also pure states, and it shares the same reduced density on the reference because it have not been changed, and the Wuhan theorem tells us that there is basically a unique purification. They can be related by some isometry, so that means you can find some good isometry, which I call VD, is from C back to A, and would approximately recover your omega C R to the original purified state with some epsilon, because this epsilon is that our state is not exactly pure, but almost pure.
Epsilon, right? Phi r is equal to omega r, that's also up to
Epsilon, yes.
The line above also.
So this is exactly, this is the reference side. So
V sub D.
V here.
It's the line below, so that's VD, right?
Yes, you're right. Sorry, I have too many V's.
Yeah.
So yeah, that's the purpose I want to emphasize this another V. Okay, so then what's the meaning of this V sub D? It actually tells us how to do decoding, how to recover the channel outputs to your inputs. So from this VD, you can guess what you should put here as a decoder. And then you can see that's how good we can do quantum communication, depending on how good our channel output is decoupled with the environment. This is also natural because if you are really not leaking any information to the environment, that means your information should be faithfully sent through. So then what's the quantum decoupling tells us that by choosing some good local unitary, you want to have a good decoupling. And this good local unitary basically tells us how to do encoder here. So this is basically the idea in a paper by Hayden and Corser with Odesky, Andreas Winter, and let me check this. I remember there's another author, and Jung Yat. So this is their 2007 paper. They use this decoupling approach for proving the famous Lloyd-Schur-Devetak theorem for quantum communication, for quantum capacitive channel. Okay, so that's how the quantum decoupling matters in this process. So now the question is, how well we can really do decoupling given the channel and the input states. So here comes a theorem by Dubris and Corser in 2010. So what they do is, in information theory, if you don't know how to find a good encoder or find a good unitary, then starting from Shannon, what we do is we do random coding, right? So they first put a unitary here on A. We want to consider the distance to some decoupled tensor product state. They want this distance estimate how large is distance in an expected way by taking the expectation of this U in the Haar measure. So that's the idea of random coding. And by normalization constants, they estimate this quantity to be upper bounded by some exponential -1/2, some conditional H2 entropy of the input state rho, and then H2 entropy of a state omega. So that's their estimate. So the idea of random coding is, if you know the right-hand side is small, by probability you know there exists some good unitary, make this distance small because the expectation is small. Okay, so that's their what do they call a one-shot decoupling theorem. So
What's A prime?
yeah, let me explain that. So here, what's this omega? What's this state? So this omega state is nothing but just the choice state of the channel. So you input the maximal entangled states into the channel with identity on a dummy reference system. So this is choice state. And then this omega E is nothing but, so this will be A prime E, because here you want in defining Choi matrix, you want to double the input system. And this omega E is nothing but the reduced density of that. And it can also be written just as the channel output on the complete mixed state. So why it has to be this state so? Now if you look at here, we have some random unitary rotation. So if you look at this term, you can view it as a random matrix. And this thing is nothing but its expectation. So this inequality from probability sense of view is in this large deviation regime. You want to estimate a random matrix, how far it's away from its mean in the expected sense, and in the trace norm, because that's a meaningful norm in information theory and also application. So this is this state. And how about this H2? So this H2 is a special case of this sandwich Ranye condition entropy. That's the special case introduced, also called collision condition entropy. It's defined to be -2 log, and here we have some informal taking trace of rho AR, and we insert some sigma -1/2 power, and to take informal of sigma, which is a density only on R. So that's the H2 conditional entropy. So this is what they prove. So the meaning of the right-hand side, if you look at here, is that if you have the quantity up to your normalization constant, if you use the log of dimension subtracting H2 of conditional entropy of rho, this tells you how correlated rho is.
So R is E, right? In your formula, R is E.
Yeah, sorry. Here E is R. So I want to consider for rho, if you are on omega, then your environment is E. Thanks for correcting this. So this part, with some normalization and with the negative side, tells you how correlated your rho is. And how about this channel part? The channel part, also with some normalization constants, this tells you how noisy the channel is. So these estimates in the right intuition shows that how well you can decouple your input depending on two counter force. One is how correlated your original bipartite input is. If your original bipartite input is very correlated, your channel is very noiseless, you are not going to disjoin any correlation. And also depending on how noisy your channel is, if your channel is just a partial trace, it's just the full trace or completely polarizing, you can just disjoin everything. So this two entropy summation really shows is the going counter force between the two. And then the question is this estimates good enough?
I think you want omega.
Yeah, sorry, omega. Right. The omega is the choice state of channel which you uniquely decide the channel. So the goal is, of course, in information theory, always just going to the IID setting. In the IID setting, we need to consider, let me denote this, this expectation to be, this notation basically is decoupling, expected decoupling error. Now in the IID setting, we want to consider n use of the states and the n use of the channel. Let me specify this definition. So of course we have expectation, and then we now have n copy of the channel, n copy of the states, and we want is approximating n tensor of the product states. And the key here is that in this random unitary, we have to use the joint, big joint unitary on A copy of A. So this is really the U of AN. So this idea goes back here is that we want to really allow joint encoding between many U's of a channel. Otherwise, there's no asymptotic behavior. So that's the quantity in the information theory care about. And with their estimates, so the goal is really to show this arrow will goes to 0 if sum of the two entropy is strictly positive. But here in the information limits, always you have the standard entropy, don't have the two entropy. Unfortunately, this standard entropy is smaller than the two entropy. So you can see that the estimate, a priori this estimate is not good enough, because if you know this is strictly positive, then you apply it for n use of the channel and the states, then you have exponential decay. But what we really want is a weaker, a smaller quantity positive will be sufficient. That means their estimates, this estimate itself is not enough. By the way, this standard entropy, conditional entropy is just the joint entropy, Shannon entropy, joint von Neumann entropy subtracting the conditional part. Okay. So then how they save this? The idea is to using some technique called smoothing. Basically, they introduce some perturbation of this entropy, the two conditional entropy, by taking a optimization of all the states rho prime very close to rho, and then consider the conditional entropy, conditional two entropy of rho prime. So it's taking some smoothing or perturbation. And with that, they can correct in their estimate here by adding some epsilon and plus some perturbation factor, perturbation term. And why this will help? Because that by asymptotic equipartition property, you know that in the ID copy, this one, if you apply n copy, this is the leading term is same as the entropy, and plus some low order term with.
Could you raise the board a little bit?
Yeah, sorry, I didn't notice that. Yeah. Thanks for the reminder. And then in the ID limits, the linear term, the leading term is same as entropy, and then it has some lower order term. So from here, they can show, if now take this decoupling arrow and take a logarithm, so you are caring about its exponents and the averaging by number of use of channel, and take a limit and this should be greater than sum of the two entropy. In particular, this will be exponential decay if these two entropy sum up to be positive. But I would like to call this one more specifically is the eventually exponential decay. The reason is that you really need to have a large n. After that, you know, okay, the exponent is positive, so we have exponential decay. For practical reason, this is not really very good because think about you want to do quantum communication. You want to say, okay, I can accept arrow up to 0.01, but I want to know how large the n I would need to do the joint encoding there, so that at least theoretically we can achieve that. Actually, how to find this U, there are some other tools you can specify more concrete U, but you really want to know how many channels I need to use so that I can design my experiments. Of course, you don't want to say for sufficiently large n, I should be able to do that for experiments. So, so that's what we do is trying to improve these estimates to get more concrete decay here. Okay, so that's the results I want to mention. I can just correct him based on their statements. So first, this is Chen Dubris self. And then what we're trying to do here is instead of go smoothing, we can go some alpha rank conditional entropy. with the alpha between 0 and 1, and this here we have some alpha prime, which is the conjugate index. And then this is the same. Here, let me give the definition of this H alpha. So it's also an infimum. By that. So it's just some a continuous one parameter generalization of conditional entropy, but also connecting with the H2. And the good thing about this one, we have to lose a little bit more factor, some constants, but that's fine. So the good thing about this one is it will converge to the standard H when alpha goes to 1. Then, so how this continuity is going to help? Now, if we denote this one as alpha, the rate at alpha parameter, so R alpha. So now, if we know the sum of the standard entropy is strictly positive, then we know that there should exist some alpha strictly greater than 1 such that the R alpha here should be strictly positive. Then by our estimates, if you now look at the IID setting, we have immediately exponential decay by this rate R alpha. Of course, later you can even just run a supreme of this alpha to have a optimal estimate. So this will goes to 0 exponentially right from n equal to 1. And the good thing about this expression here, this is explicit, so that if you say I want the arrow to be small, 0.01, and with this expression you can compute by hands at least theoretically how large n you should exist a good encoding scheme. So that's the improvements here. So for the rest of time, I want to then briefly mention what's in the proof. That's basically the other part of the talk, which is the complex interpolation. Okay, before that, any questions? Okay, so the idea of complex interpolation coming from this Ries-Thorens theorem. Suppose you have some linear map from LP function space to some LP function space. Its norm can be upper bounded by the same map from LP0 to LP0 and multiply LP from LP1 to LP1, and we need the P is inside the interval P0 and P1, and we want Banach space, so these two P are between 1 and infinity. And here we also need some power in the product, and this theta is nothing but the convex making one of P a convex combination of the other two parameters. So this is Ries-Thorens theorem, and this theorem later is called complex interpolation method because it's basically a corollary of Hadamard's 3 lemma that you can control if you have an analytic function and the theta is here in the real line, you can control this value by looking at the boundary of the standard strip. So that's the complex. Why it's called complex interpolation, because you use complex variable method. So I will not give the formal definition of interpolation, but instead, I just want to mention this idea goes far away beyond the standard LP space, and it actually has been used to define what is called non-commutative vector value LP space. That's what these things actually are. So this is actually can be expressed by, so the quantity, this infimum here can be expressed by some operator space norm of Shelton 1 on the conditional part and the Shelton alpha on the A. This is what Pizier introduced in his 97 monograph. And recently there is a very nice survey trying to just expanding Pizier's construction just for this case, which is finite dimensional case. Of course, Pizier was interested in more general polynomial algebra setting, but it turns out that after 20 years, even just the finite dimensional matrix, the Shelton class case, become very useful in quantum information. So that complex interpolation method also apply to such norm. So that's our tool. So now I will very briefly illustrate the proof idea. So the key things in this proof, in this theorem, is that what is the map, right? So you want to really find a map representing the mechanism of decoupling. So here is a very simple observation. If you apply a channel to a bipartite state, you can write it as first the product of the choice states of the channel together with the input row, and pairing with the maximal entangled state between A and A prime. And this is up to a normalization constant true. So this is a simple observation. With that, what we're trying to do is defining such map. The theta is from the matrix on AR and the matrix on A prime E. So one is for the input states, one is for the choice states. And it goes to some function on the unitary group, but taking the matrix value on environments and the reference. How this map is defined, we just take the two inputs, rho and omega, and this should be a function, so I take a point from the unitary group. I define this one just by this pairing, but with a U rotation. By the observation, this is nothing but the random matrix we care about. And then, if we further define the theta bubble to be theta subtracting its expectation, which outputs a constant function with matrix value, with matrix mean, then what we really need to prove is this theta bubble from Shelton 1, the R, Shelton alpha A, times, this is a bi-input map, bilinear map. What we really need to show is this map from these two norms, which is the right-hand side of our estimates, 2, the L1 of Shelton 1 so the estimates can be translated to be such map has a norm less than 2 for all alpha from 1 to 2. By this construction, we basically translate proving these maps now. And then with complex interpolation, we just need to care about the boundary value. So alpha equal to 1, this is very simple, just triangle inequality. And alpha equal to 2, you may notice that's almost Dubris work. But they only do positive operator. A key point for this interpolation, you have to have estimate for the entire space. So we extend the positive to general operator. That's why we lose this 4/3 constants a little bit. So with their proof plus a little bit more. And the rest is by complex interpolation. So that's basically a complex interpolation proof of our results. And I have half a minute I just want to mention. After I find the solution, I realized this is the first question my PhD advisor gave me during my PhD study. I feel lucky that I'll be able to come back to this question after 12 years and solve it. And for that, I would like to conclude. Thank you.
Any questions? Okay, well, let's thank Lee. Oh,
Yes, quick comment. So, this decoupling was a key too, right? When we want to do, especially one-shot information theory and all that.
Right.
And then came these slew of papers from Anshu et al. With the convex split lemma and position-based decoupling
Right.
and decoding. And then they don't need decoupling anymore, right? So can you, I'm just talking about, can you say something about using techniques, these sort of techniques in there?
Yes, thanks for this question. So the original talk title is more general in quantum information because I want to also mention that this method, complex interpolation method, also works for convex splitting in the single partite, multi-partite. So this works perfectly well, but you have to use another entropy term, which is just the sandwich relative entropy. So you basically, it's the same spirit that you have some L2 estimate come from sort of independence, some L1 estimates always easy, triangle inequality, and interpolate that. It's the key is how to express that convex splitting problem. You want to find a good map. You want to find a good map representing its magnetism, and that is worked perfectly well. Yeah, that's also work with Haozhong.
any other questions? And let's thank Lee again.